طيب, Bismillahirrahmanirrahim. So we're still talking about Ethernet. We talked about the way that we represent the destination address in the frame. And this, as we said before, this destination address can take three different forms, whether it's a unicast address. If it's a unicast address, then we use the format of the physical address, in the sense of dividing the address into two parts: the organizational unique identifier and the device unique identifier, or the vendor assigned identifier. If the unicast has an unknown address from the perspective of what? Who checks for this address to deliver the frame? A hub does not check for the address. That was the reason for my question. I don't want you to get so the hub does not check for. Hub deals with with analog signals. It does not deal with addresses or frames at all. It's a physical layer device. Okay? So the switch is the one that will check for the destination address. Or multicast address. And for multicast, again, the switch, because the hub is by default is going to broadcast, right?
Yes.
So the hub does not check any destination address at all. It just replicates the physical signal on all the ports without checking anything. Okay? So unicast and multicast, these are from the perspective of a switch. A switch processes the frame in the digital domain, extracts the destination address, reads that destination address, and based on that, it delivers, or it sends the signal on a specific port, on one single port. And we'll see how this is done in details today. Multicast, on the other side, you can send the signal on maybe more than one port at the same time, depending on the number of groups in the multicast address. So one address can refer to more than one device at the same time. This is what multicast means. It facilitates the communication between one person and group of people. Not broadcast, because broadcast one to all. Multicast one to many in general.
So can the switch have a destination of a hub, because hub will have
No, the hub does not have an address.
Yeah.
Hub does not have an address. It's not a destination for anything. Hub is just a device that replicates. It's just a multi-port repeater. Does not have any address.
I know, but not all the addresses or VCs on that hub. Just some group of.
No, hub does not multicast by default. Well, in order for you to multicast, you have to process. You have to know who belongs to this address. So you need to know the address. Hub doesn't know the address at all. Okay.
Switch then hub. I mean, if the switch is connected to a hub and that hub has.
Yeah, in that case, the switch is going to send on a specific port. If that port is connected to a hub is going to take this signal as is, and it's going to replicate it on all the output ports of the hub.
Okay.
That's how it works.
Yeah.
Okay, so.
So it's okay, because I'm sending to a multicast, like a group of IP.
No. But multicast here refers to an address, okay, that represents multiple devices or multiple nodes connected to that multicast group. So multicast talks about a group of people, okay? In that case, the MAC address or the physical address refers by default to group of people, to multiple nodes, okay? What you are trying to say now is that I can have like a switch to send to a hub, and the hub then delivers to this group of people. This is hard coding a multicast group using physical topology. It doesn't work this way. Okay? Supposedly, the switch will process the destination address, and based on that, it knows that it should send this frame, because it belongs to a specific multicast group, it should send this to port 1 and 3 and 5. That's it.
Okay.
Or 2 and 3, and that's it. Okay? So this is done through processing, and the destination address is going to tell the switch that.
How can we specify the destination address that the address is multiple? Like we should put a lot, multiple addresses, destination addresses in the same field? Can't happen.
No. The way that this happens is as follows. The way multicast group is established is that a node wanting to communicate to a group of people,
Yes.
it needs to first say, I want to communicate in this group.
Yeah.
Okay? Who wants to join? Okay? And then each node that is interested to join will say, I want to join. Then the switch will take this join request, and then it will update its table that this multicast address, okay, now has one joining. Okay, after some time, another person says, okay, I want to join this multicast address. Then the switch will say, oh, okay, so now I will add you as another person in the table. So when the source tries to send to this multicast address, the switch will know from the table that this person and this person who are connected on port 1 and port 3, those are interested to take that frame. So the switch will automatically send on these two ports. So the switch will learn, and we'll see now how the switch learns.
So initially there is a broadcast. There is a broadcast initially for...
Yes, so initially multicast, it gets learned through the broadcast. We will see now. In order for you to learn, okay, you have to broadcast first until you know who is connected on which port. Okay, we'll talk about that now. So, but initially you don't have this information, so you have to learn it. Okay. Of course, the third type of address is the broadcast address, which is all ones. It does not have any structure or any parts of the address. It's just all F's and okay. The other important field is the type, and as we said, type of a protocol, but in Ethernet it's called type. In PPP, if you remember, it's called protocol, but it's the same. It refers to the same thing, and this refers to the protocol in the physical. There is no protocol. Network layer. So we said that in each layer we have to, when we have the frame, we need to, when we send it to the upper layer, we need to send it to a specific protocol, because in the upper layer there might be IP, IPX, AppleTalk, different protocols. So which one should I send it to? Okay? And as we said before, all the protocols in the upper layer will be running as a service or as embedded software running on the router. So I need to know which one should I deliver it to. And from the data layer, from the data link layer perspective, when I send it to the network layer, who should I send it to? Should I send it to IP? Similar to when we talked about IP, we said that the IP should figure out when it sends to the transport layer which protocol it should send it to. يعني لما أحب أتكلم عن network layer بالعربي، لما أحب أتكلم عن network layer أتكلم عن مين؟ Which protocol should I send it to? Okay, so this is what this field tells me. Okay. The type, this type field will have different values. So, for example, if it has hexadecimal digits 0600, this indicates the Xerox network layer protocol. If it has 0800 hexadecimal, then this refers to IP. So 99% of the cases will have 0800 to indicate that I'm sending to the upper layer to IP protocol. Or 0806, which refers to a protocol in the network layer, which is called address resolution protocol. We'll talk about that probably today or maybe next time. Okay, so a switch, we talked about a hub. and we said that the hop is multi-port repeater, it doesn't do any intelligence. It doesn't have any intelligence. Switch on the other side does have some intelligence. Switch is a layer 2, and when I say layer 2, this means that it automatically contains layer 1. So it does encoding, it does signaling, it has to regenerate the analog signal again. So in order for you to process the frame in the digital domain to extract the the destination address, you have to regenerate the signal when you try to send it again, which means that you have to have a physical layer. So it's like the switch is something like this. So you receive first on the phi, and then you send it up to the data link layer. You process. Once you're done, then you have to reframe using the data link layer, and then you have to regenerate the signal using phi layer, and then you send it on a specific port. This port, you know it here when you do the processing. When you do the processing, you know which port you send it to. Then you have to reframe using the destination address, which is the same. You don't change the physical address in that case. And then you send it to the phi layer, which will generate the actual signal. Okay? So that's how it works. By default, the switch ports are full duplex, which means that you can send and receive at the same time on that port. What will happen is that the switch will store both packets, and then it will deal with one of them at a time. So in which case, one will be received and will be delivered on another port, and the other one will be sent on that port. So it knows that I cannot send and receive instantaneously at the same time, so it processes each one and then it sends each one accordingly. So by default, each port is full duplex, which means you can send and receive at the same time. Multiple devices on the switch can communicate at a time, otherwise collision will happen. So if you have multiple devices, then two devices are not allowed to send, otherwise collision will happen. So the port can have multiple choices in terms of speed. So one port can be 100 megabits per second, which means that this port can communicate either using 10 megabits per second or 100. Based on what? Based on the device that's connected to it. If that device understands 100, then we'll communicate using 100. If you understand only 10, then we'll use 10. Okay? The 1000 megabits per second gigabit Ethernet is also common. Sometimes you see the switch ports, they have mixed speeds. That happens sometimes. You see that most of the ports are 10, 100, but there is one or two ports, they have 1000 on it, which means that if you want to communicate gigabit Ethernet, you have to connect to this particular port. Okay? So these speeds are adjusted using some clocks, specific clocks, and some slot time, which we will discuss in a minute now. Okay. As we said, a switch is a learning device because at some point you need to know, I need to know the port is, well, initially the port is connected to a device, but I need to know the physical address of that device. So in order for you to know this physical address, you know it by learning, which means that at the beginning, this source, this node wants to send to this particular destination. Okay, so it sends a frame which has a destination address of 3333, and this is the source address, and it sends the frame. The port converts the signal that comes on this port into a digital, and it knows that this signal arrived on this port. So you can detect the signal. You can easily do that. Detecting power level, which means that I have a signal, I'll receive the signal, convert it to digital. So now I know that this signal is coming from port 1. So what information do I get? That this signal has a source address of 1111. So now I know that the machine 1111 is connected on port 1. So once I know this piece of information, I put it in the table. So I will add that port 1 is connected to 1111. So that's one piece of information that I learned so far. And then I will send the frame. Well, in order for me to send the frame, let's see. Destination address. Let's look at the table.
It's not there.
It's not there. What do I do?
Broadcast.
Whenever a frame enters the switch, the source address will be stored, and then I will ask myself, do I have this MAC address in the table? I don't. I will downgrade myself in that case to act as a hub instantaneously. Okay? So remember that, unlike router doesn't do that. Router will check first what?
It's routing table.
It's routing table. There is no route for this destination. What do I do next? أيوة برافو عليكي. First, do I have a default gateway? If I have a default route, then I send it through the default route. If I don't have a default route, then discard.
Default route means I'm checking the nodes on other network.
Yes, there is a default route that gets me outside.
Yes.
Okay, if I don't have this default route, this means that this packet came here by mistake, and I have no choice but to drop it. Okay, or maybe my routing table was not yet updated by the routing protocol, which is running in the background.
Yes.
So I have no choice but to drop it, and later on, hopefully, the routing protocol will, like OSPF or RIP, will update my table. But until this happens, I cannot take the decision to broadcast it. Why? It makes sense in that case. Because you know what happens when you broadcast on a router? You potentially broadcast on the entire internet, right? Or on a very large network.
So
Whereas
exceed the time.
لا, it's a big overhead. When you send on all the ports of a router, the router will send, it will go to all routers, and it will.
It won't go because it will exceed the time to the.
Not necessarily, but I'm flooding it. It's like I'm flooding the internet with unnecessary packets. Okay, so it doesn't make sense. But here, when I send a broadcast, I'm broadcasting on a LAN.
I'm sure I will find it.
Yeah, so I'm broadcasting on a LAN, so that's reasonable. I have on the LAN maybe 100 devices or something. It's okay. It's not a big deal. And this is my only way to learn anyway. I have no other way. But on the network layer, I cannot do that. Anyway, so in that case, I will broadcast. So in that case, I will send on all ports, and for sure, I'm sure that I will hit the destination at one point. Okay, so in terms of delivery, the frame will be delivered to all of them. Only this one will consume it. Okay, all the other ones we say that they overhear, but they will discard it anyway, because if 2222 receives that, it will check the destination physical address 3333. It does not match my physical address. I will discard it. This is not a hub. This is not a switch. It will not do the same. It will not broadcast. This is a host. A host is different. Okay. So this one will discard. This one will discard. Only this one will consume, which means it will send it to the network layer. The network layer will send it hopefully to the. Will check the IP address. The IP address matches, so it sends it to the transport layer. Transport layer will process it. Will know that the application is running. Will go up to the application. And now the application says, okay, everything is fine. I need to send back something or some feedback message. For example, you have HTTP HTTP works as request reply.
Yeah.
TCP works as request reply, something like that. You have to send an acknowledgement. At some point, we know that it's for sure going to happen that this node will send back some reply of some sort, okay, which will be represented using a frame with a source address of 3333 and a destination address of 1111. Okay? So this will probably trigger a feedback or acknowledgement or a response from HTTP or something like that that will come back from this node to this node. It will have a destination address of 1111 and it will have a source address of 3333. Now, only then, the switch will learn that the 3333 exists on port 6. So it will put in the table, port 6 has 3333. So hopefully next time, when 1111 tries to send any other message, it will not be broadcast anymore. It will go to a specific port. Okay? So, but at the beginning, I have to broadcast for some time until I learn which node or which physical address is connected to which port. Okay? Any questions so far? So that's this is how the switch works and how it learns. Some very important concepts that Ethernet uses to calculate its speed, and it calculates some specification like the minimum frame size and so on, which are explained in the next few slides. The first one is what we call interframe spacing. Well, there is a limitation from, so normally I would send Ethernet frames one after the other, okay? So I will send the first frame, which will contain, starting from the start frame, end frame, and in the middle I have the header, which will contain the destination address, source address, and all the fields, and then the data itself, and then the trailer, which will contain the frame check sequence, and all of this. Okay, so I send that. Now, someone is trying to send me a frame. Okay, so now I need to switch. Remember, the data link layer is implemented partially in hardware and software. So I need to switch my hardware circuits from sending something to receiving something. That hardware has some certain limitation that it needs some time to turn on and turn off receiving and sending and so on. So that takes time. So in order to compensate for this time, Ethernet defines what we call interframe spacing. Interframe spacing compensates for the limitation of processing by sending frames and receiving frames. Okay? So I need to have certain gap in order to allow me to clear the transmission process and prepare myself for the receiving process. Okay? Or the other way around. So I have to have, between each frame, I have to have interframe spacing. Wireless has the same thing. It's like your antenna now is transmitting something, and now you want the antenna to receive something. In order to adjust your hardware for an antenna to send or receive, it takes time. This is based on hardware limitation. This time could be in nanoseconds. Okay, it's a very, very short time, but it has to be there. In fact, in wireless, it's more complicated. The time is of course, is a little bit larger, and you have multiple interframe spacing types. You have different types of interframe spacing, but that's another story. So Ethernet devices must allow minimum idle periods. This idle periods is idle for transmission, but it's not idle for the hardware. The hardware has to do something.
Yes.
But for the transmission, this is a limitation. You cannot send anything or receive anything in this gap. Okay? This is a limitation for me to adjust myself. So it's idle for communication, but it's not idle for the hardware. And this happens regardless whether we're talking about the hub, we're talking about the switch, we're talking about anything, whether it's half duplex, full duplex, anything. This is required for the recovery time of the hardware between sending and receiving frames. So that's required. So what is the duration of this interframe spacing or interframe gap? Well, Ethernet defines that this is done through experimentation. There is no formula or there is no magic equation that we use to calculate the duration of the interframe spacing. The Ethernet in the standards defines, and this is defined by certain people through some experimental studies, they define this interframe spacing to be 96 bit times. The bit time is defined as a generic thing because they cannot say it's 1 nanosecond or 2 nanoseconds and leave it at that. Why? Because Ethernet can work in different speeds. So in 1 nanosecond, in the gigabit Ethernet, you can send more bits than in the 100 megabits per second or something. So in order to refer to something generic that works in every type of Ethernet, we resort to using what we call bit time. Okay? So the bit time is defined from the speed, which the bit time is the speed or the one cycle of the clock that you use for the different speeds of Ethernet. For example, if you have 10 megabits per second, 10 megabits per second, this means that you can send 10 times 2 to the power 10 bits per second, right? In 1 second. This means that how much, what is the actual duration in terms of time for one cycle? Okay? Or for 1 bit. Okay? What is the actual duration of 1 bit in that case? Or the maximum speed of the clock? It's simply 1 over بالضبط. It's simply 1 over this speed. And for simplicity, we can just say this is 1 over 10 times 10 to the power 6. يعني just to keep it simple. ماشي? Which is 1 or 10 to the power minus 7. Okay, so 10 to the power minus 7 seconds. Okay, 10 to the power minus 7 seconds, which is 0.1 microsecond. Okay, 0.1 microsecond. So the duration of the interframe spacing is 96 of this duration. Okay, which means 0.1 times 96, which is a 9.6 microseconds. As simple as that. 96 bit times. 96, the smallest duration of 1 bit in that particular Ethernet speed. So for this one, it's 1 for this, it's 1 over 10 to the power minus 8, okay, which in that case is 0.01 microsecond, times the 96, which is a 0.96 microsecond or 960 nanoseconds. Multiply by 1000. Okay. Which is this time divided by 10. And of course, in 1000, it's this time divided by 10.
Yes.
Okay, so I can calculate the interframe spacing as a duration for any speed of Ethernet. The number 96 is constant for Ethernet standards regardless of the speed. Okay, so this number is fixed for all Ethernet standards. Of course, in wireless, it's more than that. But we don't care about wireless for now. For Ethernet, it's 96 bit times. And the bit time is defined by the speed. The bit time is basically 1 divided by the speed of the Ethernet. Okay? Okay.
Doctor? Now, the interframe spacing, whenever we have interframe spacing of, for example, 9.6 micron, the Ethernet frame or the hardware should be also changed from Ethernet to fast Ethernet.
Of course, it does change. Of course, the design of the circuit changes fundamentally. Of course. Of course, the hardware will be more complicated for different speeds. طبعا. Yeah. So the actual equation for interframe spacing as a duration of time in seconds is basically 96 divided by the speed. That's it. In terms of seconds, the speed 100 megabits per second, which means 100 times 10 to the power 6. And this is done in seconds.
يعني we calculated duration for any
speed.
Or receiving.
This interframe spacing is regardless of sending, receiving, anything. This is between any two frames. You have to stay idle for interframe spacing. You have to stay idle in terms of communication because the hardware is adjusting itself. Okay, so that's one important parameter that Ethernet defines. The other one is what we call slot time. So slot time is different from bit time. Remember the difference between the two. Just be accurate in taking the definitions. So here we're talking about a slot time. Slot time talks about the time that the signal, remember that, time that the signal takes to travel from one end of a maximum sized system or cable, okay, to the other side and return. What does that mean? What is that? What is the purpose of this anyway? Well, let's see. Let's try to draw the shared medium to try to understand this parameter and what it means exactly. Well, we have the shared medium and we have nodes connected to it, right? The main purpose of this is to define the time that within this time we can detect that there is a collision. Okay? So imagine that we'll take the worst case scenario. The worst case scenario is that a node which is connected on the first part of the cable is trying to send a signal. Okay? So when this node tries to send a signal, or it tries to send, in that case, it's trying to send a frame with a specific length. Okay? So this is the time, and this is the space. So here, this is the distance, and this is the time. So this node is trying to send this particular frame, and the frame has certain length. I will talk about why I mentioned the length of that frame. So now, I'm sending this frame. The frame has a length in terms of number of bits. This number of bits are being sent on the cable as a analog signal, right? The analog signal will contain the bits. So this analog signal will propagate across the line. Remember, the analog signal propagates, it takes time for the signal to propagate. So I'm going to have to draw the signal diagonal like this. Okay? Because the signal, whether this is nanoseconds or femtoseconds or whatever, it takes time to travel on the medium. Okay? So before, the worst case scenario is that before this reaches to that point, this node, as we said before, will not be able to listen to that signal, right? So it happens that this node sends a signal. So in that case, the collision will happen. So the worst case scenario is that the signal travels all the way to the end of the cable, and then the collision happens at the end of the cable, towards the end of the cable. Okay? So this is where the collision actually happens. Okay? Regardless of whoever will detect that collision, okay, this node will inform all the others using the jam signal, the jamming signal, right? So this jamming signal will travel, worst case scenario, from this point, assuming that it's detected right away. This jamming signal will have to go back to inform everyone. This jamming signal propagates across the line and it takes time, right? So in that case, this particular node will know that there is a collision here. When after the signal went all the way to the end of the cable and came back all the way to the beginning of the table of the cable, right? So this is what we call slot time.
So it is when there is a collision?
No, not necessarily that there is a collision, but slot time defines the time duration where the signal goes from one end to the other end on a maximum sized cable. Maximum sized cable in the case of Ethernet is 100 meters.
Yeah.
Yes.
Right? So it's 100 meters. This is the maximum size. So the worst case scenario is that we have 100 meter cable and the signal propagates across 100 meter and then come back. Why we define this and we call it a name as a slot time? Because this is the minimum time you need to, from the beginning of when you start sending a frame, you need to watch out for that slot time duration that there may be any collision.
Oh, okay.
You get what I mean? So during that slot time, once you start sending, you need to keep yourself alert to listen to the collision event through the jamming signal or through any other means. Okay? If you are informed, if you get a notification through jamming signal or any other method during this slot time that there was a collision, then what do? You have to abort transmission and consider this frame not delivered, and then you should try to go back to Sysma CD and start sensing the channel again to see if the channel is idle, then try to send, and so on and so forth. But this frame, you will mark it as not delivered. Okay? So what will happen in this particular scenario? Remember that this frame has been delivered here. Okay? So this node ended the frame transmission here before the collision will happen. What will this node do in that case? It will mark this frame as delivered prematurely. Remember that here we're talking about analog signals. But these analog signals, it's like you get one bit of the frame, you send it through analog signal, and get another bit, send it to this takes a delay we call it transmission time. You take one bit, convert it to signal, send it. One bit, convert to signal, send it. You may in some cases take 2 bits, but that's another story. You get 1 bit and send it. But you will spend some time until you finish sending the whole frame. So this frame, if it's too short, you won't be able to feel the collision before you finish the transmission of that frame. And this is a very funny situation, because in that case, you will have finished delivering the frame and the collision happens after that. Remember this node? For this node, the collision happened here. The collision did not happen here. For this node, the collision happened here. This is the actual time for this node when the collision happened. If I want to know when this node will feel the collision, it's actually here. This node will feel it here. Okay? Because this is when the jamming signal went back and this node was able to take this jamming signal to know that there is a collision. So this is the worst case. The worst case is that this node will know here. And that's a very important situation, because this means that if this frame is too short, here I will mark this frame as delivered, because the collision happened after that. In other words, the frame size in terms of transmission should be more than the slot time. Which means that this actually, the frame should be long enough so that the slot time will finish before I finish the transmission of the frame. Why? Because if there is a collision, then at least I know here, I will abort everything. I will abort the transmission of the whole frame. I will mark this frame as not delivered in that case. Even if it happens at the very end of at the very last bit, but at least I felt the collision before I finish delivering the frame. I need that, because I cannot eliminate the collision. This is outside of my hand, but at least I need to feel it before I finish the transmission. Because if that doesn't happen, then I will mark this frame as delivered and everything is cool, life is rosy, and which is not true, right? So you will take a wrong decision that this frame has been delivered even though it was not.
How can we extend it to be that long?
This is something that we control.
Okay.
This is what we call by minimum frame length. So we will have to have one spec in Ethernet called minimum frame length. No one is allowed to, it's like the interframe spacing. We need to have a minimum frame length. Minimum frame length is the time that's, it has to be more than the slot time. So the minimum frame length has to be more than the slot time.
But at the very beginning, we need to know the slot time.
Yeah. This is done through experimentation. It's like you get an analog signal, you send it, similar to what we did for interference spacing. This is experiment. You get analog signal, you send it across the line. The line is maximum size. You have like one line of 100 meters. You send it, you calculate the propagation time. Send it all the way and send it back. Or you can calculate the propagation time on one side multiplied by 2 to get, on the average, the one time going back and forth. So this time you know it. So you should spend some time in transmission more than this time.
Yes,
in order to feel the collision before we finish transmitting the frame. This is very important.
Yes.
Otherwise, we'll take wrong decisions. Okay? فاهم الكونسبت؟ Okay, so we'll stop here.